Hello, welcome to my channel. In this video, I'm going to be talking about equilibrium constant calculations. The first example I have here says, for the production of HI gas at a specific temperature, the equilibrium concentration of hydrogen is 2.11 mole per liter, and that of iodine gas is 1.74 mole per liter, and that of hydrogen iodide is 83.3 mole per liter. Now, the question is, what is the Kc? So to solve this, the first thing we do is to write the equilibrium constant expression. Now, if you don't know how to do this, you can watch my video before this one. I explained how to write equilibrium constant expression on that. And this is what you do. You start off by saying Kc. Sometimes you can also write it as Keq, that's equilibrium EQ. And some textbooks say Kc. So whichever one that you prefer, you can use. So Kc here will be equals to Hi. This is 2, so you have raised to power 2 all over H2. The bracket represents concentration. Multiply this by the concentration of I. Now, in this case, they gave us the concentrations at equilibrium. So you can just go ahead and substitute those numbers into this equation. The first one we have here is Hi, which is 83.3 mole per liter squared. Okay. All over the H2 is 2.11 mole per liter multiplied by 1.74 mole per liter. Now, this mole per liter here is going to cancel one of this. There's going to be 2 of this because it's squared. The second one will also cancel this, right? So the units cancel out. So for this particular constant, you're not going to be having a unit. There are cases whereby you have a unit, but for this one, they're going to cancel out. So you won't have any units for this. So now, if we do 83.3 squared, and we divide it by this. If you plug that into the calculator, this is going to give us 1890 as the answer. Okay. So for this one, ammonia was added to 0.80 liter container at a specific temperature. What is the value of the equilibrium constant when the mixture contains 0.6 mole hydrogen and 0.2 mole nitrogen gas and 0.16 mole ammonia gas at equilibrium? And we were given the equation. So in this equation, again, you start by writing out the equilibrium constant expression. So you're going to have the product over the reactant. So this multiplied by hydrogen raised to power 3. And you have this ammonia squared because you have 2 here. This one is raised to power 3 because there is 3 in front. All right, so after writing the equilibrium constant expression, the next step will then be to put in our concentration. But then if we look at the question, we were not given any concentration, okay? This is moles, number of moles. The unit for concentration is mole per liter. Therefore, we have to calculate the concentration of the molecules involved in this reaction. Start with nitrogen. And concentration is number of moles, which I'm going to represent as N, divided by that of volume in liters. So volume in liters. So your N here is, for nitrogen, is 0.2 moles. And the volume is 0.8 liters. You see it here. Okay. So 0.8 liters. And that is going to be the same for every one of them. So if you divide 0.20 by 0.8, that's going to give us 0.25. And this is mole per liter. Now we go on to hydrogen. Hydrogen here is 0.6. So N is 0.6. So we have 0.60 mole divide that by volume in liters, which is 0.80 liters. When you divide that, that is going to give us 0.75. And the unit is in moles per liter. Now we go on to ammonia. Ammonia here was given to us as 0.6. So 0.16, 0.16 mole divided by 0.80 liters. When you do that, you're going to get 0.20 mole per liter. So now that we have all the concentration, we can go ahead and put them into the equation. So Kc here is going to then be equals to nitrogen, which is 0.25, multiply that by that of hydrogen, which is 0.75. Now, before we continue, it's important to write out the units, because if they do not cancel out, you might end up having units for your Kc. So let's write that out. That of hydrogen would then be 0.75 mole per liter raised to the power of 3. Then divide that by NH3 squared, which is 0.20 squared. Okay, cool. Now, note that this is also moles per liter here, right? Mole per liter squared. Okay, so we do the calculations. Have Kc equals 0.25 moles per liter. Multiply that by 0.42. So 0.75 raised to the power of 3 is 0.4219 approximately. And this is moles cubed per liter cubed. Okay. Now this is going to be divided by 0.2 squared. 0.20 squared is going to be 0.04. And this is going to be mole squared, liter squared. Now, there are 2 of this here, and there is a total of 4. So 1 of this and this, that is 4. What we're going to do is this 2 is going to cancel out this, and you have mole per liter remaining. Okay, so it cancels that, you have mole per liter remaining. So whatever we get here, the unit is going to be mole squared per liter squared. Okay, so 0.25 multiplied by 0.4219, divide that by 0.04, and that is going to give us 2.6. Okay, why? Because what we started with is 2 significant figure, and over here the smallest significant figure is 2, so we leave it at 2 significant, and this is going to be mole squared per liter squared. Okay, that will be the units. Okay, for this example, the question says an equilibrium mixture contains 0.013 mole per liter of hydrogen gas and 0.18 mole per liter of hydrogen sulfide gas and undetermined amount of sulfur gas. The Kc is 2.4 times 10 raised to the power of -4 mole per liter. And the question now is, what is the concentration of sulfur at equilibrium? Alright, so we start by writing the expression, the Kc expression. H2 squared multiplied by the concentration of sulfur. Divide this by the concentration of H2S squared. The squares are because of the 2 in front of H2S and hydrogen. Now the next thing we do is cross multiply so as to make HX the subject, that is sulfur, the subject, okay? And if we do that, we're going to have Kc now multiplied by H2S squared equals to hydrogen squared multiplied by sulfur. assumed we just have 1 under Kc. Now, we're going to divide both sides by the hydrogen in order to have our S standing alone. So, the hydrogens on the right hand side will cancel out. Okay? So, they both cancel out and you're left with just the sulfur as the subject of the formula. So sulfur now will be, concentration of sulfur will be equals to the Kc multiplied by H2S squared divided by the hydrogen, the concentration of the hydrogen squared. Now we're going to go ahead and put the values. So 2.4 times 10 raised to the power negative 4. Multiply that by the concentration of H2S, which in this case is 0.18 mole per liter. Okay, so divide this now by the concentration of hydrogen and we're given this, which is 0.013 mole per liter, and this is also squared. Okay, so let's deal with our units first. For H2S we have squared, hydrogen we have squared, which means that their units will all both be squared, right? So these two units will cancel out. So when they cancel out, you're left with just mole per liter, which is exactly the unit we need for the concentration of sulfur. So let's go ahead and do the calculations. After multiplying and dividing, we get 0.046 mole per liter as the concentration of sulfur for this reaction. And this is the end of the video. I hope you found this helpful, and don't forget to like and subscribe to my channel. Thank you for watching.